the Meetup notes. Chris said he can introduce himself, so I will hand it over to him. Thank you.
Great, thank you. Can you hear me okay? Sounds a little strange. Yeah, anyway, big turnout. Super excited to sort of combine my love of tennis and the Australian Open with talking about one of my favorite tech topics right now. So kind of the whole goal of the talk is just to share my experiences with kind of building applications with what's effectively a modern architecture. Not quite sure where I can stand and see my laptop. So rather than sort of the traditional kind of monolithic web app, this is an app that uses microservices along with event sourcing and CQRS, and I kind of do show a little bit of a functional domain model. And then I also deploy the app with Docker, you know, a hot newfangled way of deploying applications. So trying to fit as many hot buzzwordy topics into one talk, actually. So a little bit about me. So I actually got my start programming way back in the 80s, programming in Lisp. Lisp, of course, being that sort of very early functional language back, I guess, invented back in 1958. Though by the time I started using it, it also had object-oriented features as well. So it's a very cool, sophisticated language. Then eventually ended up in the Java world, and then back in 2006 wrote the book Pojo's in Action, which was all about building apps with Spring and Hibernate, which back then were the sort of hot new technologies that were redefining enterprise Java development. And then back in 2007, I started tinkering with what was then this obscure little thing called Amazon's Elastic Compute Cloud. Like it was very much in the early days. In fact, I organized a Java meetup in Oakland, and we'd invited the Amazon evangelists to talk about their APIs. We'd had the Google guy come talk about Google Checkout, and then the Amazon guy showed up the next month, and we were expecting him to talk about APIs for buying books. And instead he talked about APIs for provisioning servers, which just blew my mind, right? And I started tinkering around with EC2, and that turned into an open source project, which turned into my startup Cloud Foundry, which was a simple Java PaaS on Amazon EC2. And then that got acquired by SpringSource back in 2009, shortly before SpringSource was acquired by VMware. And then my technology got sort of killed, but the name lives on in what is now Cloud Foundry today, but entirely different technology base. And then these days, you know, I'm working on actually a couple of different startup ideas. I do a little bit of consulting, and I have a website, Microservices.io, which is trying to turn that into a collection of patterns for building microservices. So far in the past year, I've only managed to write 3 patterns, but working on some more, which will be published shortly. So the whole kind of goal of the talk is really, first off, so I'm going to just not go into why microservices and kind of the introductory stuff, but sort of take a sort of more opinionated approach and describe why you should build event-driven microservices, what that means, and then move on to a particular way of implementing event-driven systems, namely event sourcing, and how you can design microservices with that, and then look at how CQRS, command query responsibility separation, fits into it, and then finish up with something kind of different. The whole, well, you got all these microservices, how do you go about deploying them? And that's specifically Docker. Right, so I think sort of how we sort of think about application architecture has sort of been evolving. Like for the longest time, we would build these monolithic applications, which is interesting, right? So even though these applications would actually have a logically modular design or architecture, so in case of a banking app, it would have a banking UI, and then it would have various services, for dealing with accounts, transactions, customers, and so on. At the end of the day, you'd all go package that up inside some kind of monolithic deployment unit. So if you're off in Java land, that would be a WAR file or an EAR file. Ruby land, you'd have some modular thing, and whatever it is in .NET land. So you'd sort of have all this nice logically modular architecture, but then it would just get packaged up inside this monolithic deployment unit and then deployed on some kind of server. So Tomcat, for example, or if you really get, if you don't have a choice, your boss makes you use WebSphere. And then, it talks to a browser. And then at the back, you've got some kind of monolithic or single relational database. So, I look back over the past 15 years of using enterprise Java, and most of the apps I've written have looked like this. And good reason, right? They're simple to develop. Our tools are very much oriented towards building apps like this. They're simple to test. You just launch the app, and then you can test it with Selenium or something. And then it's simple to deploy because you can just take this WAR file and then just drop it into whatever container. It's straightforward. And then if you want to scale it, you can just sort of run multiple copies behind the load balancer, like this. So, sort of standard approach. Trouble is that, this kind of doesn't scale too well, right? Like, as soon as you get to any level of complexity or any level of team size, you run into a whole bunch of problems. So you have a team of developers who are working away, and every day each developer writes 150, 200 lines of code. And then, down the line, a few years later, you're going to end up with this massive code base that tends to be incredibly intimidating to developers. I think I visited a financial services institution, and they had like 5 million lines of code. That was their web application, right? Packaged up as one monolith. And that's just not in the Java world. I mean, the Groupon, I think they talked about having millions of lines of Ruby code, Ruby on Rails code, packaged up as a monolith, right? And it's just a scary, intimidating kind of environment for developers to work in. And it's obviously a huge obstacle to continuous deployment as well. If every time you want to make one little change, you've got to redeploy this monolith, which is likely to involve a huge amount of testing because, well, it's your system, so we've got to make sure it all works, which slows you down. It also impacts developer productivity because, sucking in a massive code base into your IDE is going to slow down your IDE. It also impacts the development cycle because it really slows down the container startup. One friend of mine working for a consumer-facing website, it actually took like 3 minutes to restart his web application. So when I was talking with someone else on Monday, and it was like 20 minutes to start up one of their applications. And if that's part of your job as a developer, is to make a change, start the application, test it, and that process only takes 20 minutes, there's only a small number of cycles in one workday, and so it makes you very unproductive. And then also, the monolithic approach really just kind of is an obstacle to scaling development. You want to take a large development team and break it up into teams where each team focuses on a particular functional area, the UI team, the accounts team, the customer team, and so on. But if at the end of the day they all have to package their changes up and put them into a single monolith, that requires a lot of communication overhead and coordination and so on, so it slows things down. And then also you can have modules which have conflicting scaling requirements. So you can have an in-memory database that's very memory intensive, and also sort of in the same application have some incredibly CPU intensive image processing code, for example. So you've got two things with two very different sort of resource requirements having to be scaled in exactly the same way, which is really suboptimal. And then lastly, this monolithic approach really ties you into the technology choices that you made at the start of the project. It's very difficult to say, well, I'm going to use some new framework because I know it's better, but in order to use that framework, I have to rewrite my hundreds of thousands or millions of lines of code in order to do that. That simply will not happen, right? And so you tend to be stuck with this large application that is using legacy technology. And all these things just end up being a big mess. Anyone work on stuff like that? Yeah, kind of sucks, right? I think every so often I run into someone using EJB2 and struts 1, right? And then often in the mainframe world, there's probably people who are working on apps that were written in the 60s, and they're really worried because the devs who wrote them are like starting to die off, and really kind of stuck. So big problems. And so, what do you do about it? So the modern approach really is to sort of kind of like, one way of thinking about it is to actually use this three-dimensional model of scalability from the book The Art of Scalability. And that actually thinks of three different ways of scaling your app. So one way, I don't know if you can see that down here, is x-axis scaling. So that's horizontal duplication, running multiple identical copies of your app behind a load balancer. So that's the common, everyday kind of clustering, scaling that we think of. And then another option is to do z-axis scaling, where you still run multiple copies of your application, but then you use some attribute of the request or some attribute of the data to decide which server instance that particular request should be routed to. So that's like sharding at the database level, for example. And then the really interesting one is y-axis scaling or functional decomposition, which instead of running multiple identical copies of your app, you actually break up your app into things that have different responsibilities. So you decompose by function. And that's what this sort of newfangled microservice kind of thing is all about. It's actually a very old concept. Like, this book was written quite a long time ago, and the idea of sort of a service-oriented architecture is incredibly old. But that's kind of, the essence of microservices is really functional decomposition. But that's sort of not as sexy a term as microservices. And so, you look at a modern application, any app of any reasonable complexity, you're going to break it up into services of some kind. So you can imagine that the banking app's going to have a banking UI service, right? You could even decompose that into mini web apps, one for each functional area of the UI, and then each of the back-end services dealing, say, with different entities in your app end up being these standalone services, and each one of those can be deployed and scaled independently of one another and worked on by different teams. And then, interestingly, each service has its own database. So that database schema can evolve independently of the database schema of any of the other services. So that's sort of one modern architectural approach, right? So is to have microservices. And then the second thing kind of deals with the database layer, right? So if you think, your standard traditional app has a single monolithic sort of database. But the trouble is that sooner or later, any app of any complexity or operating at any scale is likely to run into various limitations of the relational database. So number one is scalability. Databases only relational databases only tend to scale so far, and you tend to have to scale them vertically. You can't sort of scale them horizontally. Though, sort of interestingly, if you look at kind of modern technology, like the shift from spinning hard drives to SSD, has kind of increased the capacity of a relational database quite considerably, right? Hard drives with the sort of 10 millisecond seek times have been replaced by SSDs that can support 100,000 IOPS or whatever the standard is. So, and then you've got other even more modern architectural approaches like AWS Aurora. So you've got actually reasonably scalable relational databases, but at some point you're going to kind of hit some threshold of the biggest possible instance that you can deploy, and then it gets complicated. It's also challenging to build a multiple data center, multiple active master database on relational technology as well. So building a distributed database fabric is challenging. Schema updates can be challenging. You can have, if you look at MySQL and you want to add a column to a table, it actually has to touch every row in that table, which can take a really long time for large tables. So that's a problem. And then also there's the traditional mismatch between your rich sort of object model and your flat relational schema. That problem kind of hasn't really been solved by ORM tools at all. It still exists. And then finally, relational databases don't really deal with semi-structured data, entities with a varying number of attributes very well. It's kind of a problem. And so, some of those problems you can solve by sharding relational databases, but that puts a bunch of complexity up at the application layer. And then, of course, another popular way of solving those problems is to use some form of NoSQL database. So, if you want to do text search, rather than trying to do that in the context of a relational database, you could use Solr or Elasticsearch or Cloud Search. If you're storing graph data, you could use a graph database like Neo4j. If you want to build a highly distributed, highly available database, then you could use something like Cassandra. Out of the box, you get sort of this incredibly scalable database. So, you could even end up with an architecture like this, where different modules of your application use a different kind of database, use the database type that's best suited to the needs of that particular application. Sort of the so-called polyglot persistence architecture. But what's really interesting is if you use microservices and each service has its own database, or you're using NoSQL databases, you're likely to end up with sort of some interesting distributed data management problems that you have to solve. And so I kind of want to look at a couple of them. So let's imagine, let's take something really, really simple, right? So imagine, that sort of the database that contains the official copy of your data is MySQL, but then you want to do text search, because you want to do search on product type names or descriptions or whatever. And so, pretty standard architecture. But what's interesting is you actually have to keep those two databases in sync, right? So whenever anything gets added or changed here, you have to replicate that change to Elasticsearch. And that's not, to do that with 100% reliability is actually quite difficult because you can't use two-phase commit, right? Like, this is a transactional system, but this is not, take your typical text engine. And so kind of to do it, to maintain consistency is actually quite tricky. Another problem is, say if you're using a NoSQL database like Cassandra, it's quite common to have, a sort of one table containing the official copy of your data, and then to actually have various denormalized views of that data that you can then query efficiently. Like Cassandra is basically primary key lookup only. And yes, they support some form of secondary index, but often you actually have to manually maintain your own index tables. And once again, the main table and all of the index tables have to be kept synchronized. And that is tricky to do because you don't actually have two-phase commit. And then, sort of to go back to the banking example, you might have money transfers in one database and then accounts in another database, so possibly the accounts that you're transferring money between are actually in two different database instances. And once again, trying to kind of implement a money transfer that kind of like creates a money transfer and then actually debits one account and credits the other without using two-phase commit ends up being a tricky little problem to solve. And that sort of trying to deal with those kinds of problems sort of made me sort of come to the conclusion that a good way to do that is actually with an event-driven architecture. And so the basic idea is that your application is composed of various components, which actually could be services, or they could be different modules within the same monolith, and each one of those components owns some data. And the big idea is when a component changes the data that it owns, it publishes an event. And then another component can subscribe to events and actually, when it receives an event, perform some action, like update the data that it owns, which in turn publishes some more events. And so, if you look at how you could do money transfer using an event-driven approach, here's an example, right? So, money transfer services handles a request to transfer some money. That actually creates a money transfer, which publishes an event, money transfer created event. The account service subscribes to that and can say, oh, a money transfer has been created, and then it actually modifies or debits the from account, and then publishes a new event saying that account was debited, which ends up being consumed over here, which actually changes the state of the money transferred to debited, which then publishes a new event, which gets consumed over here, changes the credits the to account, which publishes an event, which then finally marks the money transfer as actually having been completed. So we've actually managed to sort of implement this eventually consistent workflow just by publishing events, and we've updated everything without actually having to use any kind of distributed transaction. And you could use the same kind of approach with to keep Elasticsearch synchronized, so that something changes in MySQL, you publish an event, the Elasticsearch code consumes that event and updates Elasticsearch to reflect that change. So that's kind of the big idea behind event-driven architecture. And it seems kind of good, but once again, you actually end up with another problem, which is how to atomically update state, or actually atomically and reliably update state when and publish an event. So you kind of need to do two things: update something in a database and publish an event, and do both of them kind of, well, sort of with ACID kind of semantics. And that actually turns out to be somewhat of a hard problem to solve as well, in the absence of two-phase commit. So you could use two-phase commit, distributed transaction manager, both the database and the message broker participate in that same transaction, and that so that could be done. But we're sort of living in this world where two-phase commit is unfashionable, right? Or doesn't work because of the cap theorem and all of that. So you can't really use two-phase commit. The other option, which eBay have used in their system, is actually to use the data store as effectively as a message queue. So when you begin a transaction, you update state, and at the same time, within that same data store, you insert an event into a table, or insert something into an event table to actually say, you need to do something, and then commit the transaction. So you've kind of atomically updated state and sort of published an event. And then you have another process that's actually reading that event table and with a separate local transaction kind of applying that event to the destination and marking that event as having been processed. And so that's, that's an option. But that's sort of, and it's also described kind of by this paper. And they introduced the term base as an alternative to ACID. But the trouble is you actually end up sort of tangling together, tangled business logic and event publishing code. And there's actually, you can only do this if you've got a data store that basically is a relational data store, because you need to update two different tables, the sort of the entity table and the event table within a transaction. You can't do that with the standard NoSQL databases. So it's somewhat limited. So it's like, you don't want to use two-phase commit, and then the second approach is somewhat limited. And so what can you do? And so that kind of ends up leading into event sourcing, which is sort of like, the essence of what this talks about. It's kind of funny. I'm incredibly jet lagged, and I spent the day in the wine country, which just it's not good for the brain. But Yarra Valley was very nice. Had some wine, had a nice lunch. Okay, so so what's event sourcing? And the big idea here is that for each of the aggregates or entities within your system, you identify the state-changing events. So for an account, that would be something like the account's been opened, the account's been debited, the account's been credited. So those are, in the life cycle of the account, those are things that happen that change the state. And then you just define event classes. So in your code, you would have a class, account opened event, and so on. And likewise for a shopping cart, that would be like, shopping cart's been created, item added, item removed, order placed, and so on. So you kind of explicitly model the state-changing events within your system. Okay, so that's interesting. But where it gets really interesting is that instead of actually persisting the current state of an entity or an aggregate, you actually persist the events. So, instead of saying that the balance of account 101 is 450, you actually save the 3 events, like it was opened with a balance of 500, and then it was debited by or credited with 200 by 250, and then it was debited by 300. So you never actually store the current state. You store the state, the events that change the state, including the data that, the input data is actually part of the event as well. And then if you want to recreate the current state, you simply query the event store, load the events, and replay them, and that will reconstruct the current state. So it sort of turns things around. So instead of storing current state, you store the event, and then whenever you need the current state, you just replay the event. And so it's kind of like the current state is derived instead of being kind of the official version of something. And it's like, well, how does that help? But what it really translates into is, whereas before you had to do 2 things, update state, publish an event, which, as I demonstrated, is actually difficult to do atomically. With this scheme, you literally just persist events, and by implication, publish them. And so that's one thing that can be done atomically. We can always do one thing atomically, right? And so it ends up being a kind of a simple yet reliable way of implementing an event-driven architecture. So in other words, all of the components that need to change state and publish events are actually implemented using event sourcing. And in the code that I've written, a little bit of Scala code, there are like traits. There's sort of there's various different flavors for representing this. But sort of you got an aggregate or an entity trait, and that's basically the fundamental thing that any entity has to be able to do is consume an event. So there's an apply event method that takes an event and gives you back an updated entity. So it's using immutable entities, so it's trying to be functional in some form. And then there's another trait that's a command processing aggregate. So the idea is that you send an aggregate a command like do this, and it actually responds by saying, here are the sequence of events that implement the state change corresponding to what you told me to do. So if you tell me that you send in a debit command, and it will give you back a sequence consisting of the account debited event that you can then pass to apply events to update state and get back an updated aggregate. So here's the account class. So if you're familiar with Scala, you know that you have these case classes, and so there's one attribute, the current balance. Here's the code that's processing commands, so it's using pattern matching to basically do a super kind of powerful switch on the command that you're passing in. So if it's open the account command, then return just an account opened event with the initial balance. If it's a credit account command, you return an account credited event. And then the debit one's a little more interesting because it does the overdraft check, and actually if it succeeds, it returns an account debited event. Otherwise, it returns an account debit failed because you didn't have enough money. So that's the way you process commands. And then the apply side of things, which takes an event and gives you back an updated aggregate, does pattern matching again, and then uses the copy method provided by the case class to actually return a new copy of the account with its state change. So a little bit of Scala stuff in there. But it was kind of an interesting way of building a domain model with just purely immutable entities. It's worked out so far. So that's sort of the very low level. And then the way kind of requests get handled within the system, right, is so a request comes in to modify an entity. So the first thing you got to do is go to the event store, load the events for that entity, and then sort of at the kind of code level, you instantiate, using its default constructor, a new entity. And then you apply all of those events to reconstruct the current state. And then you call process command, passing in a command that's derived from the HTTP request. That gives you new events, which you then basically append into the event store. So it's sort of kind of a slightly different kind of way of doing things, very event sort of centric way of handling requests. But what's interesting is then on the other side, you can have subscribers that are listening to particular kinds of events, and when they're published by the event store, which really corresponds to someone else saving those events, they can perform new actions like update their own aggregate, which then results in more events being published, or interestingly, update some kind of view, which could be Elasticsearch or MongoDB or whatever kind of view technology makes sense. But then, of course, you might be wondering, well, I've actually got this entity, and I've performed a lot of sort of updates to it, which means that I'm going to have an awful lot of events that I have to load from the database in order to reconstruct its state. Like you can have a 10-year-old bank account, right? That's going to have an awful lot of debits and credits applied to it over the years. And the way you can optimize that is by periodically taking a snapshot of the state of the aggregate and saving that in the event store. So what that does is, so instead of having to load all events since the beginning of time, you find the most recent snapshot and then retrieve the events that have occurred after that snapshot and apply those. And so you kind of sort of have to perform, you end up retrieving fewer events. So that's kind of a handy way of optimizing things, though it's sort of not absolutely essential. Oh god, there's a bunch of gobbledygooks. Sometimes Scala code looks like something sat on the keyboard. So this is the interface for the event store. So basically it's like, there's a save method, so that saves the events for a brand new entity in the database. There's an update method that saves the new events for an existing entity in the database. And then there's various find methods. So find an entity which must exist or throw an exception, or find an entity that might exist and it returns a Scala option class for maybe. And you can see that all these methods return futures to support reactive programming. And then the style of programming, and then there's a subscribe method that consumers of events can use to actually kind of create a subscription. So that's roughly what the interface looks like. Though, actually, if you go look in the GitHub repo, it might have changed ever so slightly. So it's sort of like, well, why do this, right? But it turns out there's a bunch of benefits. So if everything you do results in events that are effectively the system of record, then by definition you actually have a very effective audit log of what actions the user has performed in your system. So if you're working in a domain where that's really important, you can use this approach as opposed to having to like implement audit logging as an afterthought, which, yeah, you forget and you end up with gaps in the audit log and so on. It also enables temporal queries because you've saved all of the events. You can actually ask the question, what was the state of this entity at a certain point in the past, right? You can just go back in time, which once again is useful in some domains. And then, you know, if you think about the architecture of modern applications, right? You know, you've got sort of the part of the system that's handling requests, and then everything that gets done by the user ends up being fed into a machine learning predictive analytics engine that can then recommend the best cat pictures to show to users. And so, you know, your machine learning component in your system can actually just subscribe to the stream of events that are coming out, and then use that to to construct better user models. And then also the fact that it actually preserves everything the users have done since the beginning of time, right? Means that you can actually, in the future, implement a requirement, a new requirement, and basically do it in a way as if you had implemented that requirement way in the past. Because you've got all the data that you can use to then sort of process with historical data to them, which you can then process with this new feature that you've implemented. So that's kind of interesting. It sort of, you know, kind of lets you more easily implement kind of new novel requirements. So that's quite good. You know, and then of course on top of this, there's a bunch of technical benefits, right? Like, you know, you can actually solve the distributed data management challenges that you get in a microservices and or NoSQL/sharded relational database architecture. So you can implement these event-driven workflows. You can have views such as Elasticsearch automatically kept up to date by subscribing to the event stream that's coming out of your application. And then it also solves the object relational mapping problem because you'll say, instead of having to store the current state, which can be, you know, which can be a complex object graph, you're storing a linear sequence of events, and usually events have a very simple, very flat structure. You know, the only sort of challenge is around saving snapshots, but you can use something like the memento pattern to actually kind of add a level of indirection between your domain model and then what gets persisted in the event store. So that's kind of good. You know, there's obviously some drawbacks, right? Like number one, this is a really weird and unfamiliar approach, and that kind of makes it difficult to adopt. There's also the risk that your events can be your kind of a history of all of your bad design decisions because, you know, you've got a system in production, right? Those events that are generated are just going to be there forever. And sometimes you might not get the events right. But the counter argument there is that the events are very much sort of based in the problem domain that you're trying to, solve, which tends to be somewhat stable, right? It's sort of the technical solution part that can have a lot of variability. But the fundamental kind of domain events, I would argue, tend to be quite stable. Sometimes, you know, with any building, whenever you're building a message-driven system, dealing with duplicate events is something that you have to manage, right? Kind of, you know, implementing at least once messaging semantics is fairly straightforward. Implementing exactly once is really, really tricky. So you end up with this kind of the message, the event store, potentially delivering duplicate events, which you might actually have to filter out. Like, so if, you know, in a consumer, you see duplicate debit events, and you just kind of, you know, summing them up, then you're going to get your math will go wrong. So you have to do things like keep track of the last event that you saw, and then discard ones whose event ID is before that. So there's various strategies that you have to use, but you have to use them, so it kind of adds complexity. And then of course the big one is we're using an eventually consistent approach. And so, for example, I mean, one use case is, so you've got, this actually happens a lot in tests because tests run really fast, much faster than humans. So imagine you write a test that updates MySQL and then queries Elasticsearch to see that that change has been replicated, right? And you could easily imagine a scenario where the test actually accesses Elasticsearch before that event has actually propagated into Elasticsearch. And that can also happen at the UI, right? Like you hit the save button, that updates an entity, and then you redirect to a URL that views that updated entity, except that the view that you're reading from hasn't actually been updated with the event that's been published. And so it's, you kind of have some interesting little problems to solve. One way of dealing with it is just to cheat at the UI level, right? So you update it, if you've got a nice rich browser app, you make the request to update the database, and then you change the UI to reflect that change, even though it hasn't actually been applied yet. But when the user then looks at it right away, they see the new state. And then eventually, when they go back to the server, you just have to hope that it's been updated. And there's a really good chance that it has been, right? But so it sounds kind of weird, but it's actually quite workable. And then another interesting thing is the way the event store works. It's all oriented around primary key-based access or lookup of individual entities. So if you want to do more complex things like which correspond to joins, that's a problem given the event store. But I'm going to talk about a solution to that in a minute. So that's kind of the event store thing, which to me, super interesting approach, right? Okay, so what does that look like, in terms of microservices? So, the most minimal microservice with this approach could actually contain a single aggregate or a single entity, right? There are various adapters for dealing with requests coming in from the outside world that turn those requests into commands which get sent to the aggregate, and which then results in events that get saved and hence published by the event store. And then at the same time, that aggregate has an event adapter that's listening to events that's basically subscribing to events that are being published by the event store and turning them into commands that are processed by the aggregate. In reality, so you could build a microservice that implements a single aggregate, but in practice, you're likely to have a group of related aggregates or entities all packaged together and deployed as a microservice. It kind of corresponds to the bounded context idea from domain-driven design. So if you look at some of the code that I've implemented, so you can see the example in GitHub. So I've got a controller that's like handling a post request to create a money transfer. So that's Spring MVC controller. That actually calls into a service, and then the service method is actually implemented using a mini little DSL that's sort of for writing event-sourced applications. And what this is saying is create a new entity of type money transfer and have it process a money transfer command, and then go off and save those events in the event store. So that's kind of a very concise way of expressing that without kind of a lot of boilerplate. That's actually worked quite well. So it's just kind of capturing this particular boilerplate. And then the money transfer, right, is another command processing aggregate. It's a case class that has process command and apply event methods. And then the various event classes are these case classes. And then, the money transfer aggregate is also subscribing to events that are published by account, and then the account, those sort of the subscribers are written in terms of this mini DSL. So it's saying whenever an account debit event is published, update the existing entity that's a money transfer whose ID is the transaction ID of the event, and have it process this record debit command. So it's go find that entity in the database, process which is going to go off and load all of the events, replay them, and then process that command, and then persist those newly generated events in the database. And so kind of Scala lets you do that in a quite concise fashion. Ooh. Okay, so that's kind of like what sort of the business logic in the apps look like, and obviously in a real app, the actual entity classes would be a lot more complicated. So I want to go back to another topic, which is, well, how do you implement queries given that the primary, the event store basically only supports primary key-based lookup? So imagine, you want to display an account and all of the recent transactions that have been applied to that account. So that's really corresponding to a join across multiple things, right? And then, to make that work in an event-sourced application, what you end up having to do is implement this pattern known as CQRS, Command Query Responsibility Separation. And the big idea here is that the business logic that I've described up until now is basically the command side of the application. It's the part of the application that's dealing with updates. And rather than overloading that application, those modules with the responsibility of doing queries or the read side, you actually make that an entirely separate module, the query side of your application, hence the term command query responsibility separation. This is responsible for updates. The other part of it is responsible for views or queries. And the way this works, of course, is that the command side, update requests are flowing in, events are being published persisted in the event store. The query side of it is actually subscribing to those events and updating one or more views, which are some kind of database, whether it's Elasticsearch, it's text search, or it could be DynamoDB or Mongo. Whatever makes sense to support the queries that the application implements. So you end up with something, microservices, sort of in the microservice architecture, you have something like this. So you have some kind of view technology. It doesn't matter. It could be Mongo, could be Neo, could be Cloud Search, Elasticsearch, could even be a relational database if that's a good fit. You have some service, and what it's responsible for is subscribing to events, processing those events, and updating the view store in whatever way makes sense. And then you have another microservice that is handling the HTTP GET requests for sort of these UI-oriented views. And that's then querying the view store that's being updated by the update side. So if this was Elasticsearch or Cloud Search, so whenever entities get changed, it's causing them to get re-indexed in the text search engine. And then on this side, it's just making a text search query, or a text search style query against Elasticsearch or Cloud Search or whatever. That's kind of the big idea. We've got sort of this real separation of responsibilities between the command side and the query side. And it lets each sort of part of the app focus on one thing and do it well. And you can get to pick whatever kind of view technology you want, or you might actually have multiple kinds of view technology. So if you wanted, for the text search bit, you use Elasticsearch. If you're storing data that's actually like a social graph, you could actually have a view in there that's actually neo for J, or if you're storing incredibly sort of complex hierarchical data structures, maybe you've got Mongo in there as well. So you could use a blend of view technologies. Some queries are handled by the text search engine, other queries are handled by the graph database, and then the third kinds of queries are handled by MongoDB. And they can all be scaled independently of one another. So in the banking application, kind of the information about an account, its current balance and recent events is actually stored in a Mongo document looking something roughly like this. And also using, in the app that I've been working on, actually using Cloud Search because it's a nice hosted text search engine in the AWS world for a bunch of text search stuff. And then I'm also using DynamoDB, primarily because it's kind of another hosted thing that, with read-write capacity that you can adjust dynamically just by, updating the UI and so on. And so, the UI, when you view an entity in the system, that ends up doing either, well, if you're doing a text search, that gets fed, that ultimately ends up as a Cloud Search query, whereas if you, and then you get a list of entities back and you click on a particular entity, that actually is the data is then being retrieved from DynamoDB using just a primary key lookup. That's all working out quite well. So, it's a pretty useful approach, right? You've got to use it in an event source-based architecture because the event store itself is only primary key-based. The fact that you've kind of separated responsibilities tends to, at least in theory, makes each part quite simple. And it lets you support multiple sort of denormalized views that are optimized for particular kinds of queries and can be scaled independently, so that's quite advantageous. Improve scalability and so on. Drawbacks, of course, is like duplication. There's also potential there's complexity is one big problem, right? It's sort of lots more moving parts and so on. There's also potential code duplication. You might have some code that really the same code needs to run in both places, but in a slightly different way. And then there's basically the problem of replication lag, right? It can take, it's taking a finite amount of time for an event to be published and for the view to be updated. And as I mentioned, the consumers of the view might have, code that's like accessing both the command side and the view side might have to be written in a way that kind of deals with any potential consistency issues. But, as I said, there's also ways of dealing with it. All right, so that's kind of event sourcing, CQRS, so kind of looked at, there's sort of a few different kind of stereotypical microservices. So there's a command side microservice, and then there are two different kinds of view-side microservices, one for updating views and another one for querying views. And then I just kind of want to talk really briefly about how all of this is getting kind of built and deployed, so sort of specifically the use of Docker. So the architecture kind of looks like this, where they've got a bunch of services. They all kind of use the event store for so they publish to the event store, they subscribe to the event store. There's also an event archiver that's purely subscribing to all of the events that are being published by the system and then actually archiving them in S3, which lets you then process them with Spark or some kind of big data technology. And then there's also an indexer that's consuming events and actually updating Cloud Search. Kind of annoying. I actually updated to Keynote, the very latest version of Keynote, which ends up with little formatting glitches in my slides, which is most annoying. Anyway, then I'm front-ending all of this as an API gateway that's implemented using Node. So the services themselves are all implemented using Scala and Spring Boot. And then I've got this super lightweight API gateway that's routing requests to the appropriate service, and that's implemented using Node. And Yeah, this has stopped working. All right. Okay, so in terms of, well, how does all this stuff get built? So I actually have a Jenkins-based deployment pipeline. So, you know, step number one is actually to build and test the microservice. So that's sort of the standard kind of thing that you'd use with Jenkins. Where it gets interesting is actually step two. So the war file was actually an executable jar file that comes out of step one, is then actually packaged up as a Docker container or as a Docker image. And then there's actually another phase that actually just starts up that Docker container and just pings the health URL just to make sure that the container is not like broken in some stupid way. And then the third step is actually to deploy that Docker image up, is to publish it in a local image registry. So every time I make a change, things flow through this build pipeline and ends up in a registry that's actually residing in S3. And what's really cool is like building a Docker image takes like 5 seconds. You know, it's like if you've ever built AMIs, you know that like that's orders of magnitude faster. And actually publishing the Docker image into the registry is actually the slowest part of the process, and that takes 25 seconds. I mean, obviously this can take a few minutes because there's a lot of testing going on, but the whole Docker side of things, unbelievably fast, which turned me into a big-time fan of, oh, it's working again, big-time fan of Docker. So, you know, like the building Docker images is actually like I kind of copy the jar file out of the Gradle build directory into a build subdirectory and then run Docker build, and you know, 5 seconds later I have this nice Docker image. Then the actual smoke test phase, I actually use the Docker daemons REST API from a test to actually create a container from the image and then start up that container and then just ping the health URL of the container just to make sure that, you know, nothing is horribly broken. And that was kind of nice. And then the publish side of things is just a matter of doing the Docker mumbo jumbo to like tag the image with the host and the port of the registry, something that just makes no sense to me at some level, and then pushing it to that registry. And as I said, that for some reason, even though it's only from an EC2 instance to S3, that still takes 25 seconds. I think it's doing computing like lots of checksums and stuff. And then what's really funny is the whole build process is actually, Jenkins is actually itself running inside a Docker image. So it's sort of like, you know, it's that movie where, you know, things of recursive reality. Yeah, Inception. So I actually got Jenkins running as a image, as a Docker container. Artifactory as itself actually is also running as a container. And they're actually both running on an EC2 instance. And then because there's a whole bunch of state that needs to be preserved when those Docker containers get recreated, I actually have an EBS volume that's got sort of Jenkins home, Gradle home, Artifactory home, and then those volumes are mounted inside the container so that I managed to preserve the persistent state of Jenkins. That's all working quite well. And then, yeah, then there's my, quote, production environment, which currently is a large EC2 instance. So it's that like a C3 extra large with 7.5 gig of memory or something like that. So all of the services are actually running on that. And my sophisticated Docker deployment tool is actually a Python script that uses the Jenkins REST API to see what images have been built, get the latest versions, looks at what's running in the actual image, and if there's a newer version, actually kind of goes through the process of pulling that image from the Docker registry, stopping the old version and restarting the new one. So that's like my 100-line Docker management utility. And I'm hoping that before the problem of before things get too complicated, like I actually need multiple EC2 instances, the Amazon's Docker container service will actually be kind of fully fleshed out. Because the other alternative is to spend a whole bunch of time figuring out how to get Kubernetes up and running, or Marathon, for example, or actually having to look at Google Compute Cloud, which kind of has a bunch of good support for Docker. So I'm hoping that I can just use the AWS EC2 container service before too long. But I've been playing around with the the preview edition, and it was pretty rough around the edges. Oh wow! So I guess that's my talk. So summary, right? Event sourcing is a great thing because it solves a whole bunch of problems with microservice architecture, and also with sort of modern database architectures that are either using partitioned or sharded SQL databases or NoSQL databases. You need to use CQRS in conjunction with event sourcing to implement the view queries. And then Docker is a great way of packaging up these microservices and deploying them. So thank you for listening. Hopefully I wasn't too incoherent. I kind of feel very weird right now. And yeah, so there's my Twitter, email, blog, and then also microservices.io. And I will happily try and attempt to answer questions. So thank you.